Hello and welcome to the third and final video session on moments. So this one condenses chapters 4.4 and 4.5 in the Year 2 Stats and Mechanics book into one. So there's a fair few worked examples, but we can obviously get there and do it with some careful attention. So to get us in the right frame of mind, as ever, I've prepared some warm-up questions for you. So here they are, 1, 2, 3, 4. Pause the video here if you've not got the worksheet in front of you and have a go at them. When you're ready to see the solutions, press play, and I'll guide you through how to get the correct answers and calculations. Righty-ho, so let's start now with question number 1. So for number 1, we're given a lot of information, yet no diagram, sadly, and this will be a fairly standard ploy the examiners use to make the questions harder. So let's try and translate this step by step into a completed diagram. So we have a uniform rod, AB, which is mentioned first of all. It's got a mass m kilograms. So let's draw this here. So that's for rod. AB means it goes from A to B. Uniform means that its mass is evenly distributed along its length. Another way of saying this is if a rod is uniform, its centre of mass will be in the middle of it. So this rod here has a mass of m, and that's going to be acting at the centre of mass, which is halfway along its length, which is 5. So I'm going to label in that its length is 5. Therefore, its centre of mass will be acting the middle of this. So I'm going to put in there the weight of it. If it's got a mass of m, the weight will be mg. Next, we're told that this rod is pivoted at the point C, which is 0.5 meters away from B. So we can add on here this point C, where it's pivoted, and we need to also include that this one is 0.5 meters away from B. So if I just add in this as well, and I'll say that's 0.5 meters from B. So that's pretty much all we need. It next asks us to find in terms of m and g the moment of the weight of a rod, this mg, about C. So moment about C, we can now go ahead and calculate it. Well, relative to C, the only force acting on this rod is its weight, mg. So the moment is the magnitude of the force, which is mg, and we multiply that by the perpendicular distance of the line of action of this force away from the pivot. So this mg is perpendicular to C, because that's a right angle. So all we need to do now is to work out this distance here, which is going to be fairly straightforward. This mg is acting at the midpoint of 5, so this is 2.5 meters along. That's 0.5. So to go from B to here to make it a full 2.5, this is going to be the extra 2 meters. So the moment about C is mg multiplied by 2, which is obviously just 2mg. And of course you need to remember to give a direction. Because this is acting downwards from C, that's going to mean it's going to be spinning round, or wanting to spin round, in an anti-clockwise direction. And so that's the first one done and dusted. 2mg anti-clockwise. Let's now have a look at question number 2. So for question 2, we again have a rod, but this time it's non-uniform. Non-uniform means the centre of mass isn't necessarily at its centre of the length. So we are told it's a rod at least, so it's a straight line, can be modelled as a straight line, and it's got length 4 meters. So let's just draw this in here. So it starts at D and goes through to E. So that's D, and this is E. And we're also told that it's 4 meters long. So let's add in that information like so. So it's positioned horizontally, like we've drawn it. The rod is pivoted at a point F, which is 1 metre away from D. So let's add that in. So I'll just draw in here that this is F. And then I'll include that this is 1 metre away from D. Add in all the information you can, even if it makes the diagram look a bit crowded. If the diagram looks too crowded, get into the habit of doing a nice big diagram to make it less crowded looking. So next, we're told that the centre of mass of a rod is 0.5 metres away from E. So we can add this information in as well. So the centre of mass is acting here. So this rod is massively weighted towards this end. So that's the centre of mass where it's acting. And we're told it's got a mass of m. Therefore, the force due to its weight is mg acting downwards at this point here, which is 0.5 metres from E. And again, because we know the distance from E, let's label that on. So that's 0.5 metres away. It's always worth investing the time doing a carefully labelled force diagram. So next, we need to find in terms of m and g the moment of a weight of a rod about F. So we're interested in finding the moment about F, this point here. So again, the only force acting is the weight, which I've labelled in this green mg. So the moment about F, we can now begin to calculate. The moment about F is going to be the force, which is just obviously mg. And we multiply that by the perpendicular distance of the line of action of this force from F. Well, again, luckily we know it's a perpendicular distance because mg, this line of action, makes a right angle with this red line. So all we need to work out now is this distance from F to G. So we know that the full length of this rod is 4 metres. This is 1 metre. That's 0.5. And from F to mg is the missing distance to make it up to a total of 4. So 1 plus a 0.5 is 1.5. 4 minus 1.5 tells us this must be 2.5 metres. And as a double check, 1 plus 2.5 plus a half does give us this total of 4. So it's mg multiplied by 2.5 metres, which just gives us 2.5 mg. And the direction this time relative to F is going to be clockwise. So this moment's a clockwise moment relative to the pivot F. Okay, so that's question 2 completed. Question 3, again, lots of information, no diagram. So same idea, let's translate this into a carefully labelled diagram in order to complete the question. So again, we have a uniform rod, AB, mass m kilograms, which is 4 metres long. So again, we're going to draw this in carefully. So it goes from A to B, and this time it is a uniform rod. So we know that the weight of it is going to be acting downwards from the middle of the rod. So we can label this in already, because we have the luxury of being told it's uniform. So that's a force acting down mg. Again, we've been told it's 4 metres long, so let's just label in from there to there is 4. And from A to mg is 2. What else are we told? Well, actually, it's resting in a horizontal position, but it's being supported by maybe 2 planks of wood or something like that. So it's been supported at C and D. So C is 1 metre away from A. So I'm just going to draw in here. That I'm going to call that C. and that's 1 metre away from A. So labelling this in here for distance, that's 1 metre away. And there's another support D, which is half a metre away from the other end B. So I'm going to call this here D. And that tiny distance at the end is just 0.5 metres. So we need to draw a force diagram for the uniform rod AB, labelling all forces and all distances. So this is where it gets a bit interesting. All forces and all distances, that's going to be a lot of labelling. So if this rod's going to be supported at C and D, there are going to be reactions from the support C and the support D, which are in effect pushing the rod up to support its own weight. So at C, we can do a line going upwards, and I'm going to call this R subscript C. So that's the reaction from C. Likewise at D, a line going upwards, I'm going to call this the reaction from D. Okay, and as well as that, if C is 1 metre from A and B is 0.5 metres, and D is 0.5 metres from B, we could also work out the distance in between these supports C and D. So in between the supports C and D, if that's 1 metre and that's 0.5, but the total length is 4, then between C and D, that's going to be 2.5 metres. The diagram's getting a bit busy now, so I'm going to be careful how I label these next bits. So if I just drop a couple of dotted lines down here, what we can do is also work out the distance of these supports from the centre of mass of the rod. So the centre of mass, because the rod's uniform, will be acting in the middle of a rod. So from A to mg is 2 metres. That's 1 metre already, and so from C to mg, that's just going to be 1 metre. And at the other end here, from B to D is 0.5 metres, and so I know therefore that from mg to the other end, which is D, is going to be the other 1.5 metres. We can always double check this by just adding up the lengths we've labelled on. So let's do that now. 1 plus 1 is 2, plus 1.5 is 3.5, plus this final 0.5 is the full 4. So there's the fully labelled force diagram that we know now. So we're going to use this next to help us in the answer to question 4, which is coming up now. So question 4 says, using the diagram we just constructed from question 3 and by taking moments, show that 1, the reaction at C is 0.6 mg newtons, and 2, the reaction at D is 0.4 mg newtons. So let's remind ourselves of the diagram we had from before. So that's where we got to. So now we need to carefully pick where to take moments about, because we want to make life as easy as we can on ourselves and to eliminate as many unknowns as possible. So let's have a think where we can take these moments from. So first one, we need to find the reaction at C. So we're not going to take moments about C, because that will eliminate anything which is going through or at C. So that will eliminate RC. So we don't want to take moments about C, because we want to find RC. So that leaves us with another 2 options. If we take moments about the centre mg, that will eliminate mg, but then we'll have to deal with RC going clockwise, which is an unknown, and RD going anti-clockwise, which again is an unknown. So if we take moments here, we'll have to deal with 2 unknowns, so that's no good. So the only other option we have is to take moments about this point D. If we take moments about point D, that'll leave us with mg, which we know essentially because we need to leave the answer in mg, so that's no problem. So it just leaves us with one unknown, rc. But we can solve equations if we only have one unknown, so we can do that. So what we're going to do for part 1 is we're going to take moments about this point D. Now, about point D, because this rod is in equilibrium, it's not tilting or falling off its supports, we know that the moments clockwise will balance exactly with the moments going anti-clockwise. So moments clockwise will equal moments going anti-clockwise. So relative to D, the moment from D, which is going clockwise, is this reaction force. So clockwise, we've got the reaction at C multiplied by the distance of the line of action of RC from D. So we need to calculate this distance from C to D. Because we were careful in labelling our force diagram from before, we know that the distance from C to D is 2.5 metres. So RC times 2.5 metres will equal the anti-clockwise moment, which we can see here is going to be this force from the weight. So the anti-clockwise moment will be due to the weight, that's mg, multiplied by the distance of the line of action of the weight from D. Well, from mg to D, that's 1.5. Okay, so we can simply rearrange this to get RC. So RC is going to be 1.5 mg divided by 2.5. You can try this on your calculator if you'd like, but essentially 1.5 divided by 2.5 gives us 0.6. So this simplifies to 0.6 mg newtons. And that's what we wanted to show. So the reaction at C is 0.6 mg newtons. For 2, again, we could take moments. The question does say take moments. So what we could do here is we could take moments about C. I'm going to give you an easier way afterwards. So moments about C. Again, clockwise moment will balance with the anti-clockwise moments. So going clockwise relative to C is going to be this mg for weight force. And so from C, this mg is going to be 1 metre away. So therefore we're going to have mg times 1, which is just mg, but I'll label mg times 1, so you know where the mg comes from. Mg times 1 will equal the anti-clockwise moment. So the anti-clockwise moment from C will be this reaction. So the moment from this reaction, RD we're trying to work out. So the anti-clockwise moment will be the size of the reaction, which is RD, multiplied by the perpendicular distance of the line of action of RD from the pivot we're taking the moments about, C. So from C to D, we can see here that's 2.5. Therefore, if we arrange this, dividing both sides by 2.5, the reaction at D will be mg times 1, just mg, divided by 2.5, which as a decimal is just 0.4. So we have 0.4 mg newtons. So that's what we have. Now I need to mention another alternative way we could have done this as well. So reaction from D is 0.4 mg. Rather than having to take moments about C, we could have just worked out the sum of the forces, the total of the forces in any given direction, for example up and down, would have equaled 0 because this system's in equilibrium. It's not moving or accelerating. So the forces going down Let's put this in a bubble so it's not disturbing anything else. Forces acting down were just the weight of a rod, which is mg. So mg would have equaled rc plus rd. We worked out rc first, which was 0.6. So mg would have been 0.6 mg plus rd. If we had rearranged this, we would have found the reaction from D is mg minus 0.6 mg, which again would have given us 0.4 mg, which we worked out a different way by taking moments. So using a combination of resolving forces in any given direction and moments gives us more versatility in order to solve problems in more ways than just one. Let's now have a look at some examples involving equilibrium with moments. So the first vector example here is finding the centre of mass of a non-uniform rod. Firstly, I need to slightly apologise for this diagram. It's saying here that this person here is sat at A. Okay, so technically this person is sat in front of A. So just a slight mislabelling. The question was made slightly informally. A is actually meant to be this point here, exactly where this person's sat. Not just behind them, but where they're sat. Apologies as well for the names. This is a very poor, immature political joke. But anyway, never mind. So Jeremy and Boris are sitting on a non-uniform plank AB. This means that its centre of mass isn't necessarily in the middle of its length. We are told it's got a mass of 25 kilograms and its length is 4 meters. The plank's pivoted at M, the midpoint of AB. So let's add on that piece of information. Because M is the midpoint of AB, then that's going to be 2 meters. Half of 4 meters is 2 meters. So we're also told that the centre of mass of AB is at C. And we're told that from A to C is 1.8. So we consider all of the mass acting from C. Now, the mass of this rod is 25 kilograms, so therefore its weight is 25 g. Boris has mass 35 kilograms, so one of these people is Boris, and the other person is Jeremy, who has mass 25 kilograms and sits at A. So let's work out who's who. So Jeremy's sitting at A, therefore this person is Jeremy. So what we'll do is we'll do a line going down here, and because Jeremy's mass is 25 kilograms, his weight will be 25 g. Boris, therefore, is the other person with weight 35 g, so I'm going to label this in as well. Where he's sat will be 35 g going downwards like so. So there's forces due to their weights, a force due to the weight of the rod itself, the beam, the plank, and also at M there'll be a reaction force going upwards. And we don't know what that reaction force is. So I'm just going to call this R subscript M. So we don't know what that is, and do we need to work it out is the question. Is there a way around it? The question ultimately just says, where must Boris sit for this plank to be horizontal? In other words, where must Boris sit for this plank to be in equilibrium? What I'm going to suggest doing here is we work out Boris's distance from the midpoint. Now, we could take moments about A, about C, about M, or about Boris. However, we know all of these weights. What we don't know is this reaction force. And so we could be tactically clever and take our moments about M. And if we do that, Rm is eliminated because the moment of Rm, because it goes through M, is 0. So let's take moments about M. Now we need some measure of Boris's distance relative to some other point. So what I'm going to say here is we could say, for example, we could be measuring distance of Boris from the centre. Let's call that distance x. So moments about m, the clockwise moments will be equal and opposite to the anti-clockwise moments. So relative to m, going clockwise will be the moment due to Boris's weight. So the moment due to Boris's weight will be the magnitude of Boris's weight, which is 35g, multiplied by the distance of this line of action of the weight from m, which is x. So 35gx. Now the force due to the weight of a plank is going to act anti-clockwise, as is the moment due to Jeremy's weight. So these two are acting anti-clockwise. So this moment will equal 25g, the force due to the weight of a plank. Now, m is the midpoint of a plank, which is 4 meters long. If from A to C is 1.8 meters, then this tiny distance here will be 2 minus 1.8, which is 0.2 meters. And so the moment due to the 25g force will be 25g multiplied by 0.2. And the moment due to Jeremy's weight will be 25g multiplied by the distance of the line of action from Jeremy's weight to the centre. Well, from A to M is 2 meters. We can now go forward and simplify this. If we notice here, all these terms have a g in them, so we can cancel off straight away a g. So we have 35x equals 25 multiplied by 0.2. Well, that's going to be 5. And then 25 multiplied by 2 is going to be 50, which is obviously 55. So therefore, x will be 55 over 35, which we can now calculate. So 35 over 55, so 55 over 35 gives us 1.57 meters to 3 different figures. So he needs to be 1.57 meters from M to 3 significant figures. Now this distance could be written in different forms. For example, we could have given Boris's distance relative to A. So we could have said something along the lines of, if A to M is 2, and that's an extra 1.57, we could have said, for example, Boris needs to be 3.57 meters from A, or we could have given his position relative to the end at B. So if from here to here is 3.57, if the whole length of this plank is 4, then this distance between Boris and the end of the plank at this end will be 4 minus 3.57, which is about 0.43 meters. So there's a few different equally valid ways we could have written the answer to this worked example 1. So there we have it. Boris needs to be sat about 1.5 meters, 1.57 meters away from the middle of this plank where it's pivoted. This question, we have a non-uniform rod again. However, this time what we need to do is to consider the fact that it has length 3 meters and we are given the weight. If you notice the difference here, there's no diagram given, and this is a common ploy examiners use to make questions harder. So what we are best doing by far is translating this worded information into a visual diagram, fully labelled. So we've got this non-uniform rod, which is 3 meters long and it has weight 20 newtons. So let's label this in. So AB means it starts at A and runs through to B. It's in a horizontal position and it rests on supports at C and D. So from A to C is 1 meter. So let's label this on. and from A to D is 2.5 meters, where D is the other support. Of course, the full length of this is 3 meters, so I'll label that on 2. The more we label, the better. So that's 3 meters. There's a support at C, which is here, and that distance is 1 meter from A. There's a support here, which we labelled as D. In fact, what I'll do, I'll just make this a bit clearer, because at the moment it looks like AC, so I'll put C in a different place where I'm labelling it. So that's for support, and this is point C, and that's point D, and that's going to be 2.5 meters away from A. Next, we're told that the magnitude of the reaction at C is 3 times the magnitude of the reaction at D. So I'm going to label on the reaction at D first of all. Just call this R subscript D. And then we can use the fact that the reaction at C is 3 times the magnitude of the reaction at D to label this one here 3 lots of RD. 3 times the reaction of D will just be 3 RD. So the reaction force in total is all in terms of reaction at D. What we need to do out here is to find the distance of the centre of mass of the rod from A. And so the centre of mass of the rod from A means the point we can assume all the mass to be acting from. So I'm going to say it's maybe somewhere between C and D. We don't know. Just pick any point. Pick there. And if the centre of mass acts at there, the weight can be considered acting from that point. So that will be a force of 20 newtons going down, because its weight is 20. And the distance of the centre of mass from A is the unknown thing we're wanting to find. So because this is the key unknown, I'm going to label this distance x. So ultimately this question is going to be solving for x. So first of all, what we can do is we can try to work out these reaction forces. And so if we consider forces up and down, okay, because this is in equilibrium, the rod isn't moving, it's stationary and isn't accelerating, and the sum of the forces going up and down is 0. There's no net force up or down. So in other words, this reaction here at C, which is 3 times the reaction of D, as the question said, plus the reaction at D itself, those are the only forces acting up, they will be equal in magnitude to the forces acting down, and the only force acting down is just the weight of this rod, which is 20. This is now easy to simplify and solve. 3RD plus RD gives us 4 lots of RD. So 4RD equals 20. Therefore, the reaction at D is 20 divided by 4, which is 5 newtons. And therefore, the reaction at C, this 3RD, will equal 15 newtons. So we can label this on now. The more we know, the better. Next, we're trying to work out the distance of the centre of mass of this rod from A. So we're trying to work out this distance here from A. So what we can do now is to take moments about a certain point. Now we're in a good position because we know all the forces. We know the weight and we know the reactions. So what we can do now is just take moments about A, if we wanted to. So once again, because it's in equilibrium, the sum of the clockwise moments will be equal and opposite to the sum of the anti-clockwise moments. So relative to A, the only clockwise moment there'll be is the moment due to the weight of the rod. The weight of the rod is 20, and its perpendicular distance away from A, this 20 and the horizontal rod are at right angles, so it's just this x distance. So 20 multiplied by x going clockwise will be equal and opposite to the sum of these moments from the reaction forces. The moment due from this 3rd is 3rd, in fact no, I'll just put the number in straight away. So it's 15 newtons, and the distance of the line of action of the 3rd force is only 1 metre away from A. And this 5 Newton force here, the 5 Newton reaction, we can see is 2.5 metres away. So that's 5 multiplied by 2.5. So therefore, x will be 15 times 1 plus 5 times 2.5. So we can calculate this now if we want. 15 times 1 is obviously just 15. 5 times 2.5. That gives us a total of 27.5. So 27.5, divide that by the 20. 1.375 metres. So to the magical 3 significant figures, that's 1.38 metres away from A. And that's correct to 3 significant figures. So that's all we need to do. So once again, as you can see, a carefully, fully labelled force diagram underpins being able to tackle the question confidently and accurately. We now need to talk about a concept known as tilting. So tilting is something we've all experienced, whether it be unfortunately tilting and falling off a chair or something like this. So what is tilting? Well, we've got figure 1 and figure 2. So in figure 1, we're showing a horizontal rigid body, this beam, of a given mass, and it's at rest on 2 supports A and B. So in figure 1, what we've got is a system in equilibrium. Figure 2 shows the same rigid body at the point of tilting about pivot B. So in figure 1, where the system's in equilibrium, there's going to be 3 forces acting. So there's going to be a reaction at A, a reaction force at B. So a reaction at A and reaction at B will both be supporting the weight of this body, this bar or beam. And this bar, beam or rod, whatever it might be, will obviously have a weight. So the weight will be acting downwards somewhere along its length, and its weight would be mg. Now imagine though that the supports are in different places. Now obviously if we move A and B closer to the left, at some point the beam will want to tip or tilt downwards. So obviously if we move A and B enough to the left, the weight won't be supported over here, so it just might fall down and onto the floor or something. At this crucial point where it's about to tilt, what would happen is the side of the bar here at A would be at the point of leaving A. So we'd have this sort of scenario here where it'd be on the verge of sort of going up like this, but obviously not quite doing so. If it were to tilt, it'd be going and lifting up like so. Now, if it were to do that and rotate up at that end and down at the other, then there would be a pivot at B. So it'd still be supported at B, and it would just be on the verge of leaving A. So at the point of tilting, the reaction at A would become 0. Because this beam would just be about to leave A and tilt upwards into the air. And then therefore, the whole weight would be supported about this point B, which should be the point about the rod would be turning or tilting. So when something is about to tilt, a system's about to tilt, one of the initial supporting forces, whether it be a reaction or a tension, is on the verge of vanishing. And that's how you can think of what tilting is. It's the critical point. It's a critical point where if a system is on the point of tilting, it's when a supporting force is on the point of vanishing. In other words, the supporting force is about to become 0 newtons. In this case, the reaction at A tends towards 0, just as this rod is about to tilt. Let's have a look at a couple of worked examples now to just reinforce this concept of tilting. So worked example 1 about tilting. We have a uniform beam, AB, of length 16 meters and mass 45. So let's pause here and just fill in what we know. So from A to B is 16 meters. So let's label this on. That's 16. Now it's going to be, because it's uniform, we'll have a centre of mass half the way along. So half the way along will be 8 meters. So that's 8. The full length is 16. That's A. That's B. And the centre of mass is here. Acting downwards is the weight. Its mass is 45 kilograms, so the weight will be 45 G. So it's resting on supports at positions C and D, and we're told that from A to C is 5 meters, so I'm just going to draw on C here. So from A to C we're told is 5 meters. Let's add this on as well. And from C to D is another 9 meters. And so if A to C is here, from C to D will be another 9 meters. So I'm going to put D here somewhere. Then labelling on that from C to D was 9 meters. We can add this information on like so. And if the full length is 16, that bit's 5 and that bit's 9, so far we have 14 meters, and so we need an extra 2 meters to go from D to B to complete the entire length of this beam. So these two supports of these symbols here I've got, which are like chevrons, arrows. So now it says, when a child stands at A, the beam is on the point of tilting about C. So I need to just draw in some sort of child, which is balancing at A. It says, when that happens, the beam is on the point of tilting about C. About C means it's going to rotate about this point C. So what's going to happen is the weight of this child is going to make the beam about to tilt downwards like this, and so this end will be wanting to tilt up. So we need to find the mass of this child. So obviously if a child is stood at A or is at A, the force due to the weight of a child will be the mass of a child, m, multiplied by g. So it goes back to the concept of tilting. So let's just add this in. So because system is about to tilt, which force is going to vanish? Well, we've almost labelled all forces on, of course, but because the beam's been supported at C and D, what that's saying is there's going to be two reaction forces at C and at D. So there's going to be a reaction at C and a reaction at D. But because it's about to tilt, if this tilts down and this tilts up, what will happen is the beam will lift up and away from the support at D. And so if this support ends up not being in contact with the beam, the reaction from D will vanish at the point this beam tilts. So because the system's about to tilt, we can assume that the reaction from D is about to vanish. In other words, assume RD is equal to 0. Label on to begin with, then afterwards make the link that it's about to vanish, therefore make it equal to 0. So what we need to do next is to find the mass of a child by taking moments about a carefully considered point. We want to work out the mass of a child. That's the one unknown we have to stomach. That's what we need to deal with. So that's one unknown. We need to eliminate RC because we don't know the reaction at C. Okay? So if we take moments about C, that will conveniently eliminate the need to know what the reaction at C is. Therefore, the best place to take moments here is about C. So, moments about C. As ever, the clockwise moments will be equal and opposite to the anti-clockwise moments. So, relative to C, what's going to be acting in a clockwise direction? Well, going in a clockwise direction will be this weight of the uniform beam. So that's going to be the weight of it, which is 45g, multiplied by its distance from C. So that's not been labelled on, but with a bit of thinking we can work this out easily enough. So what's this distance here? Well, from A to the midpoint is 8. We've been told that from A to C is 5. Therefore, from C to the midpoint is the extra 3 meters. So we can add this in and use it in the calculation. So 45g multiplied by 3, going clockwise, will equal the anti-clockwise moments. Now, because RD is going to vanish, there's only one other force to consider, only one force going anti-clockwise, and this is due to the child's weight at A. So the child's rate is mg, and the perpendicular distance of the line of action of a child's weight from C, where we're taking the pivot, is 5 meters, as we can see. So the moment due to the child's weight is mg multiplied by 5. Because we have g on both sides of this equation, we can now eliminate g from both sides. We can cancel it off. So what we have next is 45 multiplied by 3, which is 135. That equals m times 5, which is obviously 5m. So therefore the mass of a child, m, will just be 135 divided by 5, which is 27 kilograms. Let's now have a look at one more worked example before we have some practice ourselves. This question, again, you'll notice, is very much where we've not been given a diagram, which, like I said before, is just an easy way for the examiner to really challenge you. So let's just add information as we go. So again, we've got this non-uniform rod, AB, of length 10 and weight 40. So let's just draw this in. So we're going from A to B. Its length is 10 meters. And its weight's 40. Now, because it's not uniform, we don't know that it's acting at a point 5 meters away from A and B. We can't assume it's at the midpoint. So what else are we told? Well, we're told here that it's been suspended from a pair of light cables attached to C and D. So these cables will be supporting it upwards. So maybe it's like dangling from 2 ropes or something like this. So we're told that from A to C is 3 meters. So we can do a line going up at C. So if that's going to be point C, we can call this, because it's going to be a cable, we can call this the reaction at C. And like it says here, that's 3 meters away from point A. So let's label this on. It's also suspended from D, where from B to D is 2 meters. And so D is 2 meters away from the end where B is, so we can draw this on as well easily enough, like so. So that's going to be at D, get it nice and straight. And label on that that's 2 meters away from B. So because it's 10 meters long, from A to C is 3 meters, and D to B is 2 meters, we know that the distance between these two cables must be of a missing 5 meters, because 3 plus 5 plus 2 gives us the 10. So what we need to do is to find the distance of the centre of mass of this rod from A. Now we don't know where it is. I'm going to guess. I don't know, but I'm going to guess. You just need to make a guess. But it's somewhere between C and D. I'm going to guess that the centre of mass is, I don't know, maybe here somewhere. And that's going to be acting downwards. And it's got a weight of 40, and so the weight will be acting down with a force of 40 from that point. We want to find the distance of the centre of mass of the rod from A, so importantly we're interested in the distance from A to this point here. So I'm going to call this distance here, rather unremarkably, I'm just going to call it X. So it says here, afterwards as well, when a weight of 25 newtons is hung from A, the rod is on the point of rotating. So let's add this information on as well. So there's a 25 Newton force now attached to A. It's on the point of rotating. So if adding an extra force down here makes it about to rotate, that's implying that it's about to rotate in this direction. This 25 Newton force is on the verge of pushing it down at this end, which will therefore make the rod push up at the other end. So it's going to tilt in an anti-clockwise direction. It's going to tilt that way. So we can add this in to our reasoning. So because the system's about to tilt, that means one of these forces is about to become 0. So just consider it carefully and you're fine. If it tilts down, C will be the pivot, it'll be spinning about C. And if this end comes up, at some point, this cable will go slack because this beam is going upwards, and so there'll be no need for it to be supported by this cable. And when this cable begins to go slack, that's when the reaction or the tension in this cable will become 0. So when it's about to tilt, RD is about to become 0. In hindsight, maybe I should call this TC and TD because these will be tensions, but a force by any other name would still be a force. So it should be tensions, but there you go. So RD is going to be about to vanish. So we can add this in as well, because on the point of tilting. So next we need to pick a point to take moments about. We need to pick the point carefully so that we're not going to be disabled by not knowing one of these pieces of information. We know the weight of the rod, we know the weight attached to A. What we don't know is the reaction force at C, the tension at C. So what would be a good idea would be to take moments about C so that this force we don't know, this tension, doesn't matter anyway because there's no moment due to this tension because it's going through C as it is. So take moments about C. Obviously, as ever, the clockwise sum of moments equals the anti-clockwise sum. So relative to C, what forces are going this way? Well, it's just this 40 Newton force actually. So what we need to do is calculate the distance from here to there. And we know actually now that this is going to be x. So what we can do here though is we can relate this distance here to x and 3. And so if x is all the way along, but from A to C is 3, then from C to the centre of mass will be x minus 3. So we can use that to our advantage and plug it into our calculations. So based on that, the moment due to the weight of the beam, the rod, from C is going to be the size of its weight, which is 40, multiplied by the distance of this 40 Newton force from C, which we just calculated relative to x and 3 is just x minus 3. So 40 lots of x minus 3 will equal the sum of the anti-clockwise moments around C. So relative to C, the only anti-clockwise moment in action is going to be the weight here, which is 25 newtons. So it's going to be 25 multiplied by the distance of the line of action of this 25 Newton force from C. You can see here that the distance of this force from C is this 3 meters. So the moment due to this force is 25 multiplied by 3. We can now just expand the brackets and simplify and solve. 40 times x is 40x. 40 multiplied by negative 3 is negative 120. And 25 times 3 is 75. If we add 120 to both sides now, we get 195. Therefore, x, which is what we're wanting to find, the distance of the centre of mass from A, will be 195 divided by 40, which we can work out simply enough. So 195 divided by 40 is 4.88 meters to 3 sig figs. We've done worked examples, so now it's over for you to try some. So the suggested exercises I'd suggest you have a go at are these. So based off the first couple of worked examples, exercise 4D, try at least questions 5, 6, 7 and 8 on page 81 and 82. Then to get used to the tilting questions, as a bare minimum, try questions 5, question 6 and question 7 from 4E, which starts on page 84. Hope this video has helped make more sense of these problems. If not, please do ask me in either the comments, on an email or in lesson, and do take care and keep working hard. Feel free to subscribe, that would be very nice of you. Take care, and I'll see you all very soon, I should hope. So goodbye for now, and be in touch.